Welcome to our next online lecture where we're going to talk about selection on recessive alleles, in contrast to talking about selection on the dominant allele, which we did in the last video. The first thing we need to look at are what our fitness values are going to be for the three different types of genotypes. Looking at the fitness values allows us to determine what type of selection is occurring. So remember, fitness is represented by a W. And if we want to look at the fitness of our specific genotypes, we have to represent which genotype we are looking at. So we have our WPP, our homozygous for A1 alleles, WPQ, our heterozygotes, and our WQQ individuals. In our selection for a dominant system, if you remember, the WPP was the same as WPQ, and both of those were greater than what our WQQ was. This system, it's going to be somewhat similar in that the fitness values for the WPP and the WPQ individuals are still going to be the same, but the difference this time is that the fitness value for our homozygous recessive individuals is greater than either one of those genotypes. Now this time, since we're interested in the recessive allele, or the Q allele, we're just going to take a look and see what we expect to have happen in that case. Well, if we look at what happens over time with respect to the Q allele, since it is the beneficial allele, we should expect for it to increase over time. Now the question we have is, where does it end up reaching? Remember, when we were looking at the dominant system, the frequency of the P allele, of the A1 allele, could only asymptote up to 1.0 because the Q allele would be able to hide in the heterozygotes here because the fitnesses were the same. Now in this case, when we are looking at the fitness being greatest for the recessive genotype, now our points will actually reach 1.0. Q equilibrium is 1.0. It will actually reach 1.0 in this system, and that's because it can't hide in the heterozygote. The less good allele, the A1 or the P allele, is the phenotype that is being expressed here. So this genotype can be removed from the system as easily as that genotype. So you can see that we're only going to be left eventually with WQQ individuals. So the next question should be, what is going to be the frequency of Q in that next generation? Well, we're going to do the same type of thing we did with the dominant selection, where we're going to see who has Q alleles and what's going to end up happening with those. In this case, we're interested about the genotypes that have a Q allele in it. So this time we're going to care about our PQ individuals, our heterozygotes, and they have a fitness of WPQ, and we're also going to get Q alleles from the QQ individuals whose fitness is QQ. And we're going to divide that by the average fitness in the system. Now, two quick points to remember is that W bar, the average fitness, is equal to P squared WPP plus 2PQ WPQ plus Q squared WQQ. So remember, all we're doing here is this is what's happening to the PP genotypes based on what their fitness is. This is what's happening to the heterozygotes, the PQ individuals, based on what their fitness is. And then this is what's happening to the Q squared individuals, or the A2 individuals, based on what the fitness for them is. The other thing to remember is that we don't put a 2 in front of our PQ here, because remember, when we look at the gametes which are produced by our heterozygous individuals, only 50% of those gametes will have a Q allele, and we don't care about the P alleles. So if you wanted to think about it, what we really have is 2PQ, WPQ here. But since only 50% of the alleles are going to be a Q allele in the gametes, we have to multiply it by 0.5, which just brings us back down to PQ, WPQ. So that's it for selection for a recessive allele. All we need is this equation, and we can figure out what it's going to be in the next generation, the frequency of Q, that is. And if we wanted to figure out our genotypes then, in that next generation, it would just be P prime squared 2P prime Q prime and Q prime squared, giving us the frequency of homozygous individuals with the A1 allele, frequency of the heterozygotes, and frequency of the A2 homozygotes. And remember, what we should be seeing is the Q allele continuously increasing until it actually reaches 1.0, and it will reach 1.0, and then we're done. Okay, so now we're going to take a look and do a problem, actually. And I want to see if you guys can figure out whether it's selection for a dominant or selection for a recessive allele. So first thing we're going to do is we need to think about our fitness values. So remember, we have WPP, fitness for the A1 homozygote, WPQ, fitness value for the heterozygotes, and WQQ, fitness for the A2 homozygotes. Now remember, we know if this is true, then it's selection for the dominants. If it's this, then we know it's selection for the recessive. A standard used in evolutionary biology is that the lowest fitness one can have is 1.0. That's the minimum fitness. So that means everybody's fitness has to go up from there if you're being selected for in the system. So in the dominant system, we would have WPP equals WPQ is greater than WQQ. Now we can represent this by saying that there is a selection coefficient. And we're going to represent that as S. And this is essentially how many more children those individuals are going to be having. So if we wanted to see what our fitness value was going to be in a dominant system, we would represent this as 1 plus S, 1 plus S, and 1.0. So again, this would be a dominant scenario. In contrast, if we did it as WPP equals WPQ is less than WQQ, we would represent this as 1.0, 1.0, 1 plus S, so we would have selection for the recessive system. Now, let's try and do a problem with this actually. Let's say we are going to look at bobcats. And we were going to look at their coats. And we had spotted bobcats and non-spotted bobcats. So we have bobcats with spotted coats and no spots. Now the first thing we would have to do is try and figure out whether this system is a dominant or a recessive system, or if it's something more complex, and which allele is dominant and which is not. So let's say that we have spots being the A1 allele, no spots being the A2 allele. So first thing we'd have to do is some breeding experiments. So we are going to cross a spotted bobcat with a spotted bobcat. And when we do this, we find out that we have about 75% of our bobcats have spots and 25% have no spots. And when we cross a not spot, sorry about that guys, we get 100% not spot. Now the most important one here is this result, because this shows us that whenever we cross not spotteds with not spotteds, we always get not spotteds. But sometimes when we cross spotted with spotted, we do get no spots. So this must tell us that not spot is recessive. And this is just going back to your basic genetics. If you don't know why that's the case, I strongly suggest you go and you look back up how Punnett squares work and how dominant and recessive systems work. That knowledge is going to be crucial to understanding what's going on here. If you look here, we have our classic 3-to-1 ratio. That tells us then that this spotted individual must have been a heterozygote, and this spotted individual must have been a heterozygote as well. Because if they were both homozygous for the spotted allele, then you would have 100% spotted. Alternatively, if one was homozygous for the spotted allele and the other one was heterozygous for the spotted allele, we would still see 100% of the kittens being spotted. Again, if this doesn't make sense to you, go back and look at your basic genetics textbook to re-understand how the ratios work and how Punnett squares work. Every one of you has had genetics, so this should be old hat for you guys. Okay, so now we know A1 is dominant, A2 is recessive. Now all we need to do is try and figure out what the selection coefficient is that's associated with either one of those alleles. So let's say we go out into the wilderness and find a bunch of different bobcats and look at how many babies they make. So when we look at spotted individuals, and we're only looking at the females here. We don't necessarily know what the fathers are, but we're okay with that. And if we look at the non-spotted individuals, we find that on average, spotted moms give birth to 6 kits over their life. Non-spotted give birth to 3 kits over their life. So now we have to try and figure out what the value of S is. Now remember, we always assume that the fitness of the least fit individual is always equal to 1. Now we know that non-spotteds are A2 individuals, and we know that spotteds are A1 dash, whatever, could be an A1 or an A1 A2. So the fitness of the Q phenotype must be lowest, and that's going to have to equal 1.0. So how can we take and get 3 kits equaling 1.0? The simplest way is to just divide their fitness by itself. So if I want to get the WQQ fitness value, that is 3 kits, and I need it to equal 1.0, the simplest thing I can do is divide it by 3 kits, and now 3 divided by 3 is 1. Now my fitness for my WPP individuals is the same as that for the WPQ individuals, and that equals 6 kits. But whatever I did to one equation, I must do to the other parts of it. So I divided WQQ by 3 kits, so I'm going to divide this by 3 kits. And so that's going to give me 2. Now, let's go back and think about what we said. WPP, WPQ, and WQQ, if they were this way, then it would be selection for the dominant, and the fitness of WPP would be 1 plus S, fitness of WPQ would be 1 plus S, fitness of WQQ would be 1. Now we can see that WPP equals 2. That has to equal 1 plus S. Therefore, S equals 1.0. So our selection coefficient is 1.0. It makes sense. Our spotted individuals have 100% times more kits than the non-spotted do. So now we're making headway. We know what our selection coefficient is, 1.0. We know that we must be selection for a dominance because we can see that not spot always leaves not spot, therefore it has to be recessive. Since spotted bobcats have more babies than non-spotted bobcats, selection must be favoring spotted bobcats. So we are now at the point where we know we are dealing with selection coefficient is 1.0, therefore WPP, WPQ, WQQ is 1 plus S, 1 plus S, 1 plus S. So this is going to be 2, 2, and 1. Now the next thing we need to do though, because if you remember our equation for what the frequency of the P allele or the A1 allele is going to be in that next generation was P squared WPP plus PQ WPQ all over W bar, which is P squared WPP plus 2PQ WPQ plus Q squared WQQ. So the next thing obviously that we have to do is try and figure out what is P and Q. So we need some data there. So we need to try and figure out how many different bobcats we have. Let's say that we have 75 spotted bobcats and we have 25 not spotted bobcats. How are we going to figure out what P equals? Well, in this case, it's probably going to be easier for us to figure out what Q equals. And the reason why is because we have a bunch of individuals here who might be homozygous or heterozygous for that P allele. These individuals we know must only be QQ. So we know that QQ is equal to 25 divided by 100 equals 0.25, and so that is Q squared. Now if I want to find Q, that's just going to be the square root of Q squared, or the square root of 0.25, which equals 0.5. If Q equals 0.5 and P equals 1 minus Q, P must also equal 0.5. So now we can try and plug and chug our values into this equation. So let's see what we end up with. Okay, we're just going to start with a fresh page here just so that we can see all of our math that we have to deal with as clearly as possible. So we're going to rewrite everything that we had. Let's start afresh up here and see if we can do the math for this. Okay, so P squared. We know that P is 0.5, so we have 0.5 squared times WPP, which is WPP is 1 plus S. Since S is 1, it's going to be multiplying it times 2. To that, we add our PQ, which is 0.5 times 0.5, and then we multiply all of that times 2. That was our frequency of the P allele, the frequency of the Q allele, and the fitness of the heterozygotes. Frequency of the P allele, frequency of the Q allele, and the fitness. Now in our denominator, we do P squared, 0.5 squared, times the fitness value, 2, plus 2 times the frequency of the P allele times the frequency of the Q allele times its fitness, which is also 2, and then to that we add the frequency of the Q allele squared, which represents our homozygous recessive, times its fitness, which is 1.0. Remember, WQQ equals 1 equals 1, therefore a 1 there. Now if we do our numerator, we're going to have 0.25 once we square it, times 2 plus 0.25 times 2. That's going to be over 0.25 times 2 plus 0.5 times 0.5 is 0.25 times 2 is 0.5 times 2 is 1. Sorry guys, that should have been a 2 there. So plus 1.0, and down here we're going to have 0.5 squared. That's going to be 0.25 times 1. So if we look at our numerator now, we have 0.5 plus 0.5 all over 0.25 times 2 is 0.5 plus 1.0 plus 0.25 times 1, 0.25. So that gives us 1.0 over 1.75. Therefore, P prime is going to equal 0.57. And that makes sense. Notice our P prime, the frequency of the P allele in the next generation, is 0.57. The frequency of the P allele, or the A1 of the generation before, was 0.5. We know that the frequency of the P allele should be increasing every generation, and it did. It increased 7% between generation 1 and generation 2, or between this generation and the next generation. So I hope that helps. We did an example. We've looked at selection for dominance and selection for the recessive. To do a problem dealing with selection for the recessive, you would just switch up the equation, which is the one we talked about earlier in this lecture. I hope that helps, and we'll see you at the next video lecture.